Hey, recording in progress.
And recording is in progress. Amazing. So, thanks, Tobias. This is an interesting way of doing lectures. And let's see. I think it's also difficult to get in and out of this building. I once forgot my cell phone almost on my way out, remembered it, then ran up to get in again. Anyways, so I'll continue from where we stopped last time, but a little bit more of background on the kind of things I was talking about last time, which is basically we have a hyperbolic space. So we start with X, the delta hyperbolic space. Okay, and to this space we attach a boundary. So what's called a visual boundary. So visual boundary of X is basically geodesic rays. Basic rays, that is some gamma from 0 infinity to X, which is geodesic. Modulo the equivalence relation being gamma 1 equivalent to gamma 2 if d gamma 1 t gamma 2 t is less than infinity. Okay, so your geodesics that pretty much are constant or less about a distance apart are the same. So this, a priori, if you look at this kind of a definition, it doesn't even feel like it's going to be a very nice space. How do you know it's compact? How do you know anything about it? But it turns out this space is compact, so you call this space delta X. And in fact, there is a compact space, that Klausov space, X bar, which is X union delta X. Okay, so there is such a compact space, and why are we interested in it? Is because any large scale map between delta hyperbolic space, so why are we interested in it? So that is the theorem why we are interested in it. Is if phi is a large scale map between hyperbolic spaces, then phi from delta X, so hyperbolic spaces, so phi is from X to Y, delta phi from phi extends to a map which is a topological map. Right? And if X is large scale equivalent to Y, then delta X is homeomorphic. Topological fact I'm saying homeomorphic to delta Y. So a priori X and Y are not homeomorphic. X and Y are not at all homeomorphic, but their visual boundaries would be homomorphic. Okay, so this is the reason why the visual boundaries and large scale maps, they fit together. So we have to understand the space, namely the compactification, by adding the boundary to your hyperbolic space. So this is our example. So actually, in the general theory of hyperbolic spaces, a general theory of coarse spaces, one looks at various compactifications and one has various theorems like this, but pretty much the intention is to use the hyperbolic spaces as our example. So before we move on, let's go to our very simple example. So what did we say so far? We said that that if gamma is pi1 of some surface where S genus of S is greater than 1, then we know that the Kelly graph of gamma, so I don't know how we wrote this, so C of gamma is large scale equivalent to the hyperbolic space. Okay, and it's not so difficult. We can consider this. So the hyperbolic space, its boundary consists of a circle. There is a circle at infinity. So although you don't see this Kelly graph, but the boundary of this weird graph is homeomorphic to the circle. So this is kind of things that you get out of our simple-minded investigation of compactification. So there are some technicalities. So even for hyperbolic space, so suppose this is the hyperbolic space in the Poincare model or whatever you like. You know that geodesics are all semicircles that intersect the boundary at right angles. Any semicircle that intersects, any circle that intersects the boundary at a right angle, that would be a geodesic. Now, how can you say that there is only, well, this is what I'm calling boundary for now, but this is precisely what happens is that you can have two geodesics like this, and they come closer and closer and closer, and that's why they define the same point at the boundary. Okay, so this is the idea of this is the necessity or desire or motivation to look at compactification as far as we are concerned, and so let's go through some functional analysis to achieve compactification. It's not so hard. So maybe I think this is anyhow not that complicated. So I'm going to take this off. Of course, compactifications are very important in many problems in mathematics, especially if you do nonlinear PDEs and all that kind of stuff. Often what you have to understand are various kind of compactifications. The theorem that I'm going to use for compactification is not always the only way in functional analysis to look at compactifications, but the ingredient in it, we'll see, does the most part of it. So what we have, on one hand, last time I was trying to do this, so this is what's called the Gelfand mark L. And as this is not going to be our main focus functional analysis, I will be little tiny bit vague about some things. So one side of this theorem is a simple thing. So if we have a locally compact space, if X is a locally compact, so this we said last time as well, this LCH is always locally compact in Hausdorff space. Then there is an algebra. It always gives us C0 of X, which is continuous functions vanishing at infinity. At infinity with soup knob. Okay, so this is a Banach space, of course. With the soup knob, it's a Banach space. But of course has two more operations. So you can take two functions. So if f, g belong to C0x, then of course you can take product, which is of course what you know. It's not rocket science. So there is multiplication, so this makes it a Banach algebra. But there is another thing which is what we call f star of x, is just the conjugate function, the complex conjugate of f of x. Okay? So these two properties make it not just a Banach algebra, but with this thing it becomes a C star algebra. And of course, multiplication of functions is commutative, so it's a commutative C star algebra. Okay? So starting with the locally compact Hausdorff space, there is always a commutative or a Banach algebra with multiplication and a star operation which satisfies something. But here are two important things to note. So suppose I say 1 vanishes at infinity. So if 1 is in C0x, then you don't have to write the 0 anymore. This basically implies that x is compact. So if this is a unital algebra, if there is the constant function 1 is in this space, then you have a compact space. And second thing which I will not prove but mention is that if C0x is separable, what does separable means? It has a countable dense subset. Okay, so if it's separable, then X is metrizable. So here there is whole gymnastics. So whatever property of X you want, you might want to see this in the algebra C0x. Okay? So what is more fascinating is the converse to this statement. So this observation is more or less trivial, but Galfand Normark say that actually the converse is true. Okay. So here is the converse statement, which is what the theorem is. So Galfand Normark says any commutative C star algebra is isomorphic to C0x for some locally compact Hausdorff space X. Okay, so this is pretty much stating the converse. And so from this algebra, one needs to find a space. So actually it's easier because we can start with any algebra, add to it. So before I go on, I'm going to just look at an example. So start with a non-unital. So So non-unital means algebra which does not have a unit, does not have one unit. Commutative C star algebra A, and then add a unit. So that is, you look at the algebra A plus, which is just A okay, so there is an obvious multiplication and everything on this algebra, so I'm not going to worry about that very much. You can come up with this. You can write what this should be. Then A plus is C of X plus, where X plus is X union infinity is the 1 point compactification of X. Okay, so that is pretty much what you need to go to get the very basic example of one-point compactification. So the thing is, I'm going to very, very vaguely describe how do you get X from the algebra A. This is what I right now going to explain is within strict mathematical sense is not perfect. But I think this is how far we will talk about this. Because otherwise we'll just spend a lot of time doing functional analysis. So there are lots and lots of nice references to this material, and any search on Google will get you a lot of information. In fact, this kind of observations led to the study of C-star algebras, because even the non-commutative one, because then people thought the non-commutative C-star algebras behave like spaces, and in some sense they do. Okay. So here, so if I say A is isomorphic to C0x, what is the X? So X is what's called the spectrum of A, which is, so I'm assuming A is unital for now, which we can always break by adding a unit to it, which is all maps, all things in dual of A. I am only putting one condition, phi 1 is 1. Okay, so this is a little bit shitty, but I don't care right now. So this space is contained in the dual. It's in fact it's contained in the dual. What am I saying? In the unit ball in the dual. Okay, because of my requirement. And then there is a theorem, which is probably what most people learn in functional analysis, which is called the Banach-Alaoglu theorem. This is the most important ingredient here. This says the unit ball in weak star topology. So unit ball in any Banach dual of any Banach space in weak star topology is compact. Okay, so this is how you get the compactness of the spectrum, because it's closed subset of a compact set. So, but here is the magic, because last time when we talked about the stone check compactification, we realized that we need, what do we need? We need axiom of choice. We need Tekhonov's theorem. The theorem, Banach-Alaoglu's theorem, this requires axiom of choice. So no matter whether you run through C-star algebra, through topology or whatever, if you want to make something like the Stonecheck's compactification, you will need axiom of choice. But what we will see is if we have something like separability, we will get a metrizable space. And in those cases, these things are not so important. In those cases, the compactification, the Banach-Alaoglu theorem can be constructed explicitly. You don't need axiom of choice. But that's the other thing. So what do we have? If you have a unital C-star algebra, then it corresponds to a compact space. And generally, if you have non-unital C-star algebra, then it corresponds to a non-compact space. So here is the requirement that we are looking for. So, so to obtain a compactification, so we'll just look at the most obvious example and then I will say more because examples are good. So we know that C0x is the C-star algebra and that corresponds to X, right? There is no problem. If we do this process, the Gathard-Neumark thing to C0x will get back X, no problem. But then there is always the CBX, which is continuous bounded functions on X. And what would that correspond to? This is again a C-star algebra. It is again commutative. So there should be a space for it. What's the space for it? Can you make a guess? You're the only person here. It is the Stonecheck's C0 of that. So it's the Stonecheck. And in fact, any subalgebra that is contained here in between them. So if I put a C-star algebra here, which contains this and is contained there, that will correspond to some compactification of X. So any C-star algebra that's in between corresponds to a compactification. All right, so far so good. This is all the functional analysis. Let's go back to geometry. Okay, here for. Okay. I think I'm very fast because I think if I don't. Maybe we should have a shorter lecture today, otherwise I'll end up saying too much. Do you have the feeling I'm talking too fast?
For me, not really.
Yeah, but
for the ones watching live, you can write in the chat. If you
actually, we forgot to turn that on, but we should try it once in a while to see if we can get the audio response.
Yes, we got the audio.
Huh?
When we were enabling audio, you were talking and we heard your echo.
Uh-huh.
So the audio works. So if the ones online watching live, you can talk if you want.
If you think I'm being too fast. Because I'm getting a feeling that I'm talking my brain out faster. rather than pausing in between, you know. It's a psychological thing. How fast you talk depends on depends on factors. Okay, so at least we are done with functional analysis. Back to geometry. And now we have to, so if we want to, so now we know our progress. Now we know what we are looking for. So we are looking to make the space X bar, which is X union the boundary that we defined, right? So what we need to find is this thing, which we presume should be, this is our commutative algebra A, and they should be contained in the one that is for the Stonecheck, so CBX, which is the Stonecheck's compactification. And of course, it should contain our thing. So if we can find such an algebra corresponding to this guy, then this will provide us all the topological means just functional analytically. So we don't have to worry about defining topology, checking compactness, anything at all. All we need to find is such an algebra. And of course, for the theorem I mentioned downstairs, you would like to check that such an algebra behaves nicely with large-scale equivalence of nodes. Okay, so here we go. So again, going to this boundary, we have an equivalence relation. So what's our equivalence relation? Is that if I have two geodesics, which are going to the same point at the boundary, right? I want to consider the point at the boundary a function which has a value at the point of the boundary. So here is an observation, and this observation corresponds to lots of problems in certainly in delta hyperbolicity for certain reasons I can explain. So choose a base point. Choose any base point. Okay, and so pick gamma 1t, gamma 2t. Okay, and what one wants to do is to say as gamma 1t and gamma 2t go to infinity, you should be able to define a function at the limit. So what we want in that sense is that f of gamma 1t minus f of gamma 2t should go to 0 as t goes to infinity. So that they both define the same function at the limit point. So this is our kind of requirement. Otherwise, so we look at all bounded functions which should have some property like that. So what's the correct way of achieving it? The correct way of achieving it is a simple observation with triangle inequality. So there is this triangle with a fixed base point. Okay? And in fact, you can now define the deficit between going from gamma 1t to gamma 2t through B and going directly from gamma 1t to gamma 2t. So that deficit is defined like this. So although I'm writing it, I will write another, sorry. So this is the deficit, this is 1/2 of distance of x gamma 1t plus distance of x gamma 2t minus distance gamma 1t gamma 2t. So this thing is a deficit between going from one point to the other directly or going through your base point. Okay? And this has a name, and what you would want is, as t goes bigger, this deficit obviously becomes bigger. As you go closer and closer to infinity, these two things remain at a bounded distance from each other because we are assuming they are converging to the same point at visual infinity, this deficit will become very, very large. And this is the key ingredient, key geometric ingredient in the construction of the algebra that we are interested in defining the space. So, just want to give this a little try. We have a lot of mass. We usually don't.
There's a question in the chat. Small x is what you called b in the in the picture. I think you called it.
Oh yeah, sure. This is one of the guys. I think it's easiest to.
Easier to do it in the graphics. Yes.
Yeah, the answer is yes. This should be b. Sorry about that. This is just because I'm going to define it with an with an x in a second.
Thank you.
Who is this?
Felix.
Felix.
So in total, 3 people are watching.
Huh?
3 people are watching,
Wow.
including me.
Almost makes me feel.
Oh, somebody's trying.
Yeah.
Probably they were shied away by the room being created quite late.
Yeah, but today
Yeah.
I have had had an interesting day with my computer and everything. So that's also why the lecture notes are not up as I would usually put them. But hopefully tonight it will be done. So my computer has to get back in action. So anyway, so people have a weird name for this deficit. They call it Gromov product. So for sake of both attribute to Gromov, probably he is the one who started using it. I don't know. But also for sake of, if you read literature elsewhere, this is what Gromov product is. So Gromov product y to z through x. So it's saying how much I have to pay more to go from y to z if I actually went through x. And this is how I should think about it. How much do I pay more? How much do I pay more to go from y to z if I went through x? Half of that is the Gromov product. Okay, and once you have the Gromov product, a simple master triangular inequality will tell you one basic property of Gromov product. So this is y, this is z, this is x. Let's suppose this is the closest point on the geodesic. So this is the geodesic from here to here. What you can see immediately from so call this point P, right? So I can write this thing as so if P is the closest point to x on phi z, and I can write this same thing as half dxy plus dy, minus dyp plus dxz minus dyz. T is Z2. So I've split this thing, since P is a point in the geodesic, I've split this thing as dy P as dz. Right? This is no problem. If as long as I stay on the geodesic, I can break one of these guys into two pieces. And by triangle inequality, so this whole thing is less than, just 1 second, I'm going right way. The triangle inequality will mean this is greater than.
Somebody raised their hand.
What happened?
Butler, Philip, Joseph, do you need something? I don't know which is the name. You can talk or write in the chat. I don't know what he wants. Maybe he just clicked around.
Okay, maybe. Let's see. Or maybe he will talk again. So, if you look at this picture, all I'm saying is I'm going to go this distance and subtract this distance. Then what can I be sure of? I can be sure of that that's bigger than. So I can write this as half dx to p plus again dx to p. Okay, and so this is p was chosen to be the shortest, closest point to x, so this is greater than equal to dx phi z. Right, because I'm adding it twice. So this is somehow the crucial. This holds for any geodesic space. No, I think I made some mistake, right? Which way should I write my triangle inequality? Sometimes when
No, the direction is okay.
no. Direction.
Oh no,
The direction is wrong. Because I was just thinking about it, and I was thinking about something else while I'm writing one thing. All this, I'm thinking about the step after. The step after is not what one should think about. So this is a crucial fact about Gromov product. The Gromov product, the deficit of going from y to z through x is always less than the distance of x to the geodesic in any geodesic space. So right now I haven't used the fact that we are on a hyperbolic space, but this will become useful. But the hyperbolic space, I think I'm not going to derive the other half. Maybe I'll just mention it. So I'll mention this other formula without deriving it, and I will put the derivation in the notes. Because I don't think one learns too much by doing this derivation in the class. It's just this tedious manipulation. So, with reference that this will be derived in the notes, I will, without doing it here, because I think it's not worth the effort. So there is another inequality, but this was for all geodesic spaces. So if x is delta hyperbolic, then there exists a delta prime such that actually delta prime is 4 times delta. In the proof we'll see that, but it's not important, such that distance of x from the geodesic yz minus what am I doing? Yeah, minus delta prime is less than the Gromov product y to z x, and is less than equal to the distance of x from the geodesic. So this is actually the whole thing that you get on a hyperbolic space. So somehow this mysterious object, this deficit, it is very nicely bounded by this geometric distance of your base point x to the geodesic on both sides. It's finitely bounded. So this is something you can think of. Such an object will be very important for large scale properties. Okay? And that's what happens. So going back to our problem that we have here in mind, where is our problem? Oh, it's gone away. I erased it, no? I think so. So let's get back and write the problem again and that we want to solve. And let's solve it. So basically I give the solution as I write. Because this is a fantastic solution. I mean, I would like to motivate the answer by giving you all kinds of hints. But to be honest, it is a clever piece of work. It's really a clever piece of work. So what one calls a Gromov function. Okay, so a continuous function f on x is called Gromov function. Gromov must be the big series function. If for every epsilon greater than 0, there exists an r greater than 0, such that. So now I will fix a base point. So it does not matter. This definition does not depend on base point, but the formulation does. So fix a base point b in x. So usually people even drop the base point at this point because they think, you guys know everything. Says that if I have y to z through the base point, this distance, if the deficit of going through the base point is bigger than r, implies see, this is the kind of thing we drew in the picture before. We said, remember when you have, I just drew this picture and I made the mistake of maybe I should have just written x here. So I will not make this mistake. If I write z here, I'll keep making the mistake of writing fy minus f. It's just too much teaching calculus over 100 years of my life that you used to write fy minus fx. If you teach so much calculus, you cannot write fy minus fx. So if you have two geodesics going like this, towards the same point in the boundary, their distance remains bounded to each other at any one time. That's our definition, right? And we have some base point here, P. And what we said that this deficit, as you go closer and closer to the boundaries, this deficit becomes bigger and bigger. But what you want, as you go closer and closer to the boundary, you want these two values to become equal. So what Gromov says is if the deficit becomes bigger than some number relative to some base point, you make the function small. That is all. That is all. So this is the class of functions that will be the algebra A in our Castagnard theorem. That's all. Okay? So now I can basically state and prove the theorem. Okay, so this is the easy part of life. All right, let's do this. Okay. I think I'm going to just state it the way I'm kind of remembering it in my head. Some people would even call this a lemma, but I'm calling it a theorem. So any Gromov function on X is bounded. Bounded, okay, that's one thing. Two, the space of all Gromov functions, all Gromov functions is an algebra closed under uniform convergence. Do I have to say anything else in it? Well, of course, the third thing is obvious, but I'll still write it as part of this. That any function which vanishes at infinity is Gromov. Right? Of course, we'll see all three of these. So once we have this, we call this space the space of all Gromov functions is denoted by CG. Okay. So actually, the only thing. Oh, yeah. Sorry, an important thing I forgot. A very important thing I forgot, because it can be compact, but compact spaces like the stone-check compactification can be very weird, right? The boundary of, if you had, so we are saying this is a boundary, but stone-check compactification is so weird, it's not it has a lot of issues. So what you want to say here is that, maybe I'll just, it should have been on the top, but I'm adding it at the end. CGX is separable. So what does that mean? By Kalfan-Naumann theorem, that the underlying space, which we don't know yet, which we will identify the corresponding space, which is the same as that, which we will prove in a bit, codes, which we haven't proved yet, is metrizable. So it's not a bizarre compactification. That's important. It's not some crazy compactification like the Stonecheck's compactification. It's a metrizable compactification. Okay, so that is the important fact. All right. So now it's a bag of tricks. It's a bag of tricks. And sometimes I forget my tricks. We'll see. So actually, how am I doing on time?
You have more than half an hour left.
More than half an hour left.
So 37 minutes or so.
Yeah, if possible, I would like to finish the early too. But we'll see, because I also don't want to drag it another time, because this is kind of self-contained topic. Right? Oh, is this thing that's making this sound?
Yes.
Oh. I was wondering why I stopped and then there is some sound. Anyways, now the mystery has been solved. So first thing is actually the 1 and 4 go together. So if you want to say, so suppose we are given f is a Gromov function. So I'm going to set some parameters. So or maybe I shouldn't have started like that. Let's fix epsilon greater than 0 and k greater than 0. We fix that. And f is a Gromov function. It belongs to the set S epsilon x. It will belong to this thing if so I have a base point. In all the discussion, we have a base point. And although I haven't said this, everything is independent of choice of base point. If you choose another base point, you will change the value of r or k or something by the distance between the two base points. There is absolutely no big deal changing the base point. Okay? So you change everything by the distance between the base point and everything is fine. Anyways, so what do we want? So we have, so f is in this set parameterized by epsilon and k if whenever yxb is greater than k implies fy minus fx is less than epsilon. So these two parameters you put it in your definition. So you make some class. Okay. Now I'm going to say that all the functions in this class. So the obvious thing is that any Gromov function is in sum as epsilon. So if I prove it for epsilon and k, I prove it for all Gromov functions. That's the argument. So now what you take is so B is the ball of radius k plus 1 at the base point. So let me draw a picture here. So we have our base point and we have a ball of a big enough radius k plus 1. And suppose x does not belong to V. So if you have a continuous function, so this is by our definition. Remember that hyperbolic spaces and so on, geodesic spaces are proper. So a ball of a bounded radius is always compact, and a continuous function on a compact set is bounded. All you have to worry about what happens if I go outside that set. Right? So I take some point outside that set and I join it, because this is again a geodesic space is our requirement for a hyperbolic space. Join it with a geodesic to the base point, and it crosses here. Crosses this ball at some point, because it will. This is a continuous function. The distance from V is a continuous function. It has to be at one point. Okay, so and that x is not in the ball, and let y be the intersection of Q with this. I don't know how to write this. It's the last point in the boundary. This is not very right way of defining it, but shall I be very, very pedantic? You can see that as the distance increases, there is a unique point at distance k plus 1 on this geodesic. That is what y is. But this is an official way of saying it, okay? It's fine. We are all grown-ups. So don't consider that as a boundary. So maybe at distance k plus 1 on the geodesic. Okay? And now what you can see is that if I look at this, what will that be? That thing is going to be k plus 1, so that is clearly greater than k. Right? And this automatically implies that f of x minus f of y is less than epsilon. But y is in this compact set, so there is an absolute maximum value of y that can happen. Also, there is a sup to y, so that means automatically that f of x is less than sup b f of y belongs to b plus epsilon. And x was any point outside your compact set, but its value is bounded. So what have we proved? The function is bounded. Okay, so this proves false. Since x was arbitrary, the series F is bounded. Alright. But this thing itself, so this is probably a little bit technical part. But this is important. As I said, it's important to know that this boundary is a metrizable space, not something weird like the Stonechecks boundary. So that's the next thing I want to prove. All the other things are basically epsilon by 3 estimates. So all these other things, even if you don't prove it, I very much guarantee you can leave this as exercise. They're epsilon by 3 estimates. By the way, I suppose all of you do these kind of mathematics, so you are familiar with epsilon by 3 estimates, right? Write something as, so if you want to know what A minus B is, you put some C in between and a D in between, and take the absolute value of A minus C in this. Okay, so now what we have is the following. We now have a ball. So we continue to work with S epsilon k. This is the reason to introduce the space S epsilon k is the format. I could have actually done it without actually using this terminology here. Right? The proof of boundedness did not use S epsilon k. The proof of the separability will use this. Okay. So what we have is that if you are on this set, we can. So if f, so, I don't know. I'm getting a little old. If f is in S epsilon k, right? This is given to you, then so I'm going to look at, to explain this, I'm going to look at continuous function on this compact set B. Continuous functions on any metrizable compact space, this is because this is part of the metric space by definition, is separable. Right? So if I restrict a function f to this, it should be approximable by some countable set here. So you can pick a countable set. So gk is countable dense. Okay, set. Yeah. So my f, when I restrict it to b, there exists g belonging to gk such that f x minus gx is less than, I don't know, epsilon for all x and b. Okay, this is by denseness here, and since I have this other estimate, fx minus fy is less than epsilon, I can pretty much with some fudge say that, but so now I'm taking these gk's in this set. So I can take gk's. That's why I think this is very tricky, but easy and tricky at the same time. So I can take this in as epsilon k if I really want to. But then I have to show. This is a little bit of trick, so I'm not going to worry about this right now. I'll come back to it. So I can then say that actually this is not just in x and b. I can go to x in all of x because of the estimate that we just proved down there, that fx minus gx is then less than say 2 epsilon. Okay, so that means my function can be approximated nicely by a countable set, at least within this range. And any Gromov function is a union, so I can take epsilon to be 1 over n and k to be n, something like that. Then I can say my Gromov functions c, g, x is contained in the union n s 1 over n. Okay. So if I have a countable basis for each n, the union will be countable. If I have a countable dense set in each n, the union will be countable, and this is a countable. This proves there is a countable dense subset in each S 1 over n, and so there is a countable. So CGX is separate. Okay, so this is a little bit of hand waving I did here, which is not such a big deal actually. Let's keep things clear. Is this clear what I have said so far? More or less.
More or less, yes.
Yeah, except that I waved my hand how I got these G's a little bit, because of course you know that this is a metrizable set, so there is a metrizable dense set here, but I am claiming that they are in here because of course I can kill them outside of B, and then they will satisfy any estimate I want, right? And so I will get that. So to B, if I'm in B and I kill them outside B, they will still belong to my by partition of unity. This is a closed subset. I can kill it outside the closed set. So this is why I can do it. But it's a little bit of technical, just arguing this partition of unity kind of thing. But you can imagine, if you have a countable dense set, you can extend it to all of X by killing it just outside of B. And those things will be in S epsilon K. So that is the point of it. Okay, so what else? So there were two more things showing that. I will probably just show one of them. It's kind of obvious that any function that vanishes at infinity is going to be in Gromov, this Gromov function algebra. So I'm not going to worry about that. I'm just going to say that if I multiply two functions, almost everything else in this kind of thing is the same logic of epsilon by K. Right? So if F and G belong to CGX, right? And then I want to say Fx Gx minus F y gy. This thing I can always estimate is less than equal to Fx gy minus Gx Gx. Do you agree with that? Because I just basically added Fx gy plus, so minus this plus Fx gy. So just add it here, right? Add 0 here, and then split it in the middle and take the common thing out. So these are the terms you get. Okay.
With G of the y.
Huh?
Then it would be G of the y, but anyway. Yeah.
Oh, did I make some mistake?
Yeah, but.
Well, because maybe I chose the wrong xy here then.
No.
Which one do you mean?
It doesn't matter.
Or you think this is y?
I think this is y.
Yeah, exactly. I think so too. Yeah, you're right. That is g of y. Good. Good, that's right. So this is standard trick. Now, if we want this to be less than equal to epsilon, so we want this to be less than epsilon, say, right? What do we have to do? We know that when so we can pick R, so pick R greater than 0 such that if your is greater than R implies gy minus gx is less than epsilon by norm f divided by 2, and similarly also for g, and f x minus fy is less than equal to epsilon by 2 large. So if you pick R such so big that both these things are satisfied, then this is less than epsilon. So of course the product of Gromov function is Gromov function. Right? Similarly, if you want to check convergence, you can take a sequence, uniformly converging sequence, and you will have to do a similar estimate, but that will be an epsilon by 3 estimate. So I don't think if it's worth the effort to do it, but I think these things are just easily verified in a few minutes. So the only tricky part was the one that I've already done, the separability and the boundiness. The other things are just, do what you think should be done and take an estimate. That's it. So now we have an algebra. So we have an algebra C0x contains our algebra CGX, and that contains the boundary function on X. So this thing represents some compact space as of now. But why should it represent the visual boundary that we are interested in? Okay, but that is pretty much how we build the thing up. When we drew the picture, we decided how we should define this algebra. That pretty much describes.
One question.
Yeah.
Why are this in this inclusion business here?
Yeah.
Between C0 and CB, you require the guy in the middle to have a 1, right?
Yes.
Okay.
Yeah.
Now it makes sense.
Yeah, because if it has no 1, then the corresponding space will not be compact. Right. So this will have 1. Obviously, this we did not check, but you can of course check. This estimate, if you have a constant function, the estimate of something, constant function minus constant function at 2 points, is equal to 0.
Yeah.
So the constant function is going to be this.
Yes,
Yeah, there is no issue with the constant function being in there. Right? So maybe a lemma. If gamma is a geodesic ray, and f belong to the Gromov functions, so we have a Gromov function, then f gamma t limit t goes to 0, t goes to infinity exists. Okay, that is what we want. That's the first thing we want. A. And B. Remember, this equivalence is called asymptotics. I forgot to say it again today. If gamma 1 is asymptotic to gamma 2, then what do you expect? Then limit t goes to infinity f of gamma 1 t equals limit t goes to infinity f of gamma 2. Okay, so that at least tells us that on visual boundary our function is well defined. So these are bounded functions which are well defined on the visual boundary. Okay. The third thing I want to say is a little bit more, that I don't want to have any other points in the boundary of gamma. Right? So if f belong to CGX is such that limit t goes to infinity f gamma t is 0 for all geodesic rays, then what should happen?
So compact domain.
Yeah, so it should not. Yeah, it vanishes as infinity. Then F belongs to C0. Okay, so that means there are no extra points. There are no more points than the Gromov points at the bottom. Alright, so none of these things are, I think, terribly difficult. Maybe the third one is a little bit. But this is a way of thinking. I think I like this way of thinking. Of course, one could have defined a topology directly on the space of X union this bounded points. Then one could have proved that this topology is a compact space, and so on. That's one way of doing it, of course, and it has been done. You can find references where it's done like that. Somehow, I think those techniques don't generalize so much. You can learn it for this, but it's not clear to me if you could use it for something else. Maybe you can. I don't know. But these techniques are very general, so why not? Okay? So, the first thing is very simple. So I'm assuming I can assume base point anywhere, so I will assume B to be gamma 0. Right? Change of base point doesn't make much difference. Then it means that the Gromov product with respect to that is minimum of P and P prime. This is just what we have already encountered. So you have, if you go to gamma, so suppose this is big and this is small something, right? So if you're going all the way there and then all the way here and then coming back, your deficit is at least this much, the minimum much. You cannot have less deficit than that. Okay, maybe I should put a half there. It's not that important. Okay, so this deficit is that big. What does that tell me? That as limit t comma t prime go to infinity, f gamma t minus f gamma t prime, this thing goes to 0. And because of this thing, you get bigger and bigger. There will be, you'll cross every k, and therefore you'll be smaller than every epsilon in our definition of Gromov function. Right? So as these become bigger than r for epsilon, then this difference will be smaller than epsilon, and you get to 0. But this means this is a Cauchy sequence in T. And since we have assumed completeness, hyperbolicity assumes completeness, it means if this sequence is Cauchy, that means limit t goes to infinity f of gamma t exists. Sorry, what I'm talking about, these are just numbers, sorry. These are just numbers. And if this is Cauchy sequence of numbers, then the limit exists. Okay, sorry. Sometimes one makes things more complicated. Just the mere thought of it. I don't know. I mean, the second step is pretty much the same thing repeated again. This time you have to see that if I take, if gamma 1 and gamma 2 are asymptotic, with some constant like distance gamma 1t, gamma 2t, is always less than sub c, right? That's what it means. Then you can say that the Gromov product, the sum base point, I don't even care, this is bigger than or equal to plus minus some constant. Maybe this is C prime. But that C prime and C are different because I might have to change the base point a little bit. So it doesn't matter. You basically see that as t goes bigger, this thing can be made as small as you want. So it basically means as t becomes bigger, f gamma 1t minus f gamma 2t, that should become smaller. It's less than epsilon equals to 0. So that proves part 2. So for all geodesics which are in the same equivalence class that define the same point at infinity, you get the same value of the function. So the function is well defined on the points coming from the visual boundary. Okay. All right. So, do I have 10 minutes, 5 minutes, or 2 minutes? 7 minutes. Actually, I could do this, but what is to be more exciting is to do the statement that I did stated at the very beginning. So if you prove this last statement, you're basically saying there are no extra points in the Gromov boundary, which I am going to maybe write in the notes now and skip it for now. Because it's not, is it terribly interesting? Actually, that's a neat proof, but I don't think the idea is something that you will ever use anywhere again. So this is also my sort of logic of dwelling on which technique. So if I dwell on some technique, I hope it's something that you'll use again. Whereas the last thing is a fun proof by contradiction. So I will write it in the notes. So in the time that we have, I will go back to our initial motivation for doing all of this. What was our motivation? Our motivation was the following theorem, which I will write again. So if phi x to y is a large scale, so I'm going to write equivalence for now. Equivalence between delta hyperbolic. So delta, you cannot write delta because one will have one delta and the other will have other delta. So I'm just writing delta still. Hyperbolic spaces, then phi induces homeomorphism on delta x to delta y. So this is the main result. I think maybe I could even stop here today and start with just, it's not a very big thing, it will probably take 10 minutes to do it. But it's something that's valuable. And then we can next time do abstract. So we'll do this proof of this theorem and then define abstract large scale geometry where we don't take any metric into account. And you can see that you can define large-scale geometry just by having a compactification. That will be one of the motivations to define abstract large-scale geometries. Okay, so let's just stop it for today. If anybody has questions, you can send it to Tobias and say, if not, then we can just stop. Right? Before we close, we ask questions.
Seems there are no questions. At least no one is talking.
Okay then. And we can just say bye-bye to all of those people there. Did you close that? Okay. Let's just close it.
Close the recording.